In this section, we're going to talk about derivative as a function. Now, in the previous section, we talked about finding the derivative at one single specific point. And we had two equations for that. So we had, let me make a note of this. Let's see, we'll put at a point, the derivative at A is the limit as x approaches a of f of x minus a f of a over x minus a. Or we could have the second equation, which was the derivative at a, which was the limit as h approached 0. And remember, h is the distance between the two x values as they get closer and closer. And so we have f of a plus h minus f of a all over h. And those were the two equations. The one that I like to use is this one because it's a little bit easier. For me it is. I mean, that's a difference of opinion from person to person. But you could also use this one for finding the derivative at a specific point. But now we're going to talk about it as a function. So now it seems reasonable to conclude that if we know the derivative of a function at every point, we could produce valuable information about the behavior of a function. So we would have the actual function, and then we could plug in points and would give us the derivative at that specific point. So that's what this definition is. It's the definition that we would be able to find the derivative as a function. And once we get that function, we could plug in different points to see what the slopes of the tangent lines are at different points. The derivative function is defined as the limit as h approaches 0 of f of x plus h minus f of x all divided by h. So we're going to walk through some examples. I'm going to show you how this works. So to find the derivative of the square root of x so that we have it in terms of a function where we could plug in any value of x we want to find the slope of the tangent line, we're going to take the limit as h approaches 0 of the function f of x plus h, which means we have to plug in x plus h here. I have x plus h underneath the square root. Then I'm going to minus f of x, which is the square root of x, and I'm going to divide by h. Once we start getting into the next few steps, what we're going to have to do is use some algebra manipulation that I can plug in 0 for h to evaluate this. However, we can't use direct substitution and limit laws as it is, which is why we have to go on and continue with some additional steps. So what I'm going to do is, for the next step, I'm going to multiply by the conjugate. Typically, when you have roots involved, not all the time, but most of the time the conjugate trick works. So I'm going to take the square root of x plus h minus the square root of x over h. And I'm going to multiply the top and the bottom by the conjugate, which is the square root of x plus h plus the square root of x. And I got to do that on the top and the bottom so that this is algebraically correct. Then when I multiply that out, on the top, I'm going to get x plus h minus x, because when I distribute, I get this times this, which is x plus h. I get this times this, which is a minus x, and the middle terms disappear because they're the same exact thing but plus or minus. Now on the bottom, I'm going to have h times the square root of x plus h plus the square root of x inside parentheses. Now on the top, when I simplify that, I have x minus x, that disappears, so I'm left with h over h times the square root of x plus h plus the square root of x all in parentheses. Now I can cross off the h on the top and the bottom, so I have 1 over the square root of x plus h plus the square root of x. And now I can plug in h is 0 and use direct substitution in the limit laws. And when I do that, I get 1 over 2 square root of x. So this is the derivative of our function square root of x at any point. So now I can use this to find out information about the graph. If I wanted to find the slope of the tangent line at, let's say, 1, and all I have to do is plug 1 in here and calculate it. If I wanted to find the derivative at x equals 5, then I just have to plug it into this function and figure it out. It's really beneficial to have the derivative as a function, and then you can plug it in at any point, as opposed to what we were doing in the previous section where we were directly finding the derivative at a specific point. Now this is the derivative at any point. Okay, let's go to the next example. We're going to find the derivative as a function of x squared minus 2x. So we're going to find the limit as h goes to 0 of f of x plus h, which means everywhere that I see x in my function, I have to plug in x plus h. So I'm going to have x plus h squared minus 2 times x plus h. So this is f of x plus h. Then I'm going to subtract my f of x. So I have x squared minus 2x, and that's all over h. Now I'm going to take x plus h and square it. So I'm going to do x squared plus 2xh plus h squared. That's my x plus h squared. Then I'm going to distribute the negative 2. So I have negative 2x minus 2h. And then I'm going to distribute this negative here in front of the x squared minus 2x. So that's going to give me a minus x squared plus 2x. And this is all over h. Okay, so now things are going to start to drop out. And if they don't, then you probably forgot to distribute a minus somewhere. So check your work if that doesn't happen. So I have an x squared here and a negative x squared here. I have a 2x here and a negative 2x that I can cross off. So what's left on top after I cross everything off, I have 2xh plus h squared minus 2h. So all of those terms have an h in them, so I'm going to factor the h out. And what's left would be 2x plus h minus 2. And I still have everything over an h. So now I have the limit as h goes to 0. I've crossed off my h's, so I'm left with 2x plus h minus 2. Now we can use direct substitution in the limit laws to plug in 0 for h, and what I get is 2x minus 2. So this is my derivative at any point of the function x. Okay, next example, we're going to do a rational function. This gets a little bit messy, but it's not hard. It's just long and messy. So I want to find the derivative of f of x equals 1 over x plus 1. So I'm going to take f of x plus h, which means everywhere I see x, I'm going to plug in x plus h. So I have 1 over x plus h plus 1. So that's my f of x plus h. Then I'm going to subtract my f of x, and it's going to be all over h. Now, to clean this up, it's a complex fraction. And so whenever you're trying to clean up a complex fraction, you take the denominators of what I like to call the smaller fractions, even though I didn't write it in, let me write it in now. This is h over 1. So these are my smaller fractions. And if I look at the common denominator for that, I'll make a note of over here. My common denominator is going to be x plus h plus 1 all times x plus 1. There's my common denominator. So I need to multiply everything by that common denominator. And when I do that, I'm left with x plus 1 minus x plus h plus 1 all over h times x plus h plus 1 times x plus 1. Okay, so I just multiplied the top and the bottom by this common denominator here. That way I clear the fractions and I'm left with x plus 1 minus the quantity x plus h plus 1 all over h times the common denominator. So now, when I clean up the top, I have an x minus x, that disappears. I have a 1 minus 1, that disappears. And I'm left with a minus h over h times x plus h plus 1 times x plus 1. Okay, now I can cross off the h's, and I'm left with the limit as h goes to 0 of negative 1 over x plus h plus 1 over times x plus 1. Now I'm in a position where I can use direct substitution. So when I plug in 0 for h, I'm going to get negative 1 over x plus 1 times x plus 1, which is x plus 1 squared. So this is the derivative of the function 1 over x plus 1 at any point. Okay, now we're going to talk about the different notations of a derivative. So let's use f of x is equal to x squared minus 2x as our example. So far, the only notation that I've showed you is this, where we have f and then what looks like a little slash up where the exponent normally would be. And then we have the notation f of x with that little slash. And our derivative would be 2x minus 2. Another way that we can write this, if we're using y notation, y equals x squared minus 2x, then we can also use the notation that looks like this, y with a little slash up there, and we'll write down that the derivative is 2x minus 2. Another notation that we could use is dy over dx. This, we would say, the derivative of y with respect to x. The independent variable would be down here, and the dependent would go upstairs. And I would write dy, or d, whatever the dependent variable is, over dx, or d with whatever the independent variable is. And then we could also write it like this. So let me actually write bullets here. There's this method, this method, this method. Okay, let's talk about another method. We could also write it like this. The derivative of x squared minus 2x with respect to x is, and then we can actually write it as 2x minus 2. So in general, using this form in general, we would say d over dx, and then inside we would write the function and then state what the derivative is. There's lots of different ways to do this. Now, lastly, I want to show you the notation for finding the derivative at a specific point, we have shown this. Let's say I wanted to find the derivative at 3. Then I would write the derivative at 3 like this. Another way we could write it is dy dx, and then you have a little line, and then you have x equals 3. So these two things are exactly the same, just different ways of writing it. Okay, now we're going to talk about graphing the derivative of a function. We know because of a previous example that the derivative of this function is 2x minus 2. But if I just looked at the graph of x squared minus 2x, and I wanted to draw a rough sketch of the derivative, here's the graph, just a rough sketch of x squared minus 2x. I know it has zeros at 0 and 2 because that's the values of x that I would plug in to get out 0 for the y value. And then by symmetry, or you can check it using the vertex formula, at x equals 1, we would know we would have a vertex. And then if I plug in the value of 1 to find the corresponding y value of the vertex, let's see, if I plug in 1, that's going to give me negative 1. So here's just a quick sketch of our parabola x squared minus 2x. If I wanted to use this graph to sketch the derivative of f of x, this is what we're going to do. I'm going to use orange. I'll use blue for increasing. And then I'll use red for 0. Okay, if I trace the graph of x squared minus 2x from left to right, I'm going to start here, and I'm using orange because I'm going to be decreasing on this interval of the graph. Right, as I trace the graph left to right, I am decreasing on the interval from minus infinity to 1. And I'll write this over here, minus infinity to 1. I'm decreasing. So that means if we're decreasing, the slope of the tangent line at that point, or the rate of change at those points along where the orange is going to be negative. So that tells me that the derivative is going to be negative, meaning less than 0, on the interval negative infinity to 1. Remember what the derivative means. It's the slope at any particular point on the function, the slope of the tangent line. So when I'm graphing the slope of the tangent lines, anywhere where the function is decreasing, the derivative should be negative. Okay, now at this point, right here at the vertex, if I imagine the tangent line that just touches that one point, that's going to be a horizontal line, which means the slope is going to be 0. So at x equals 1, my derivative should be 0. So I'm going to write it down. At f of 1 on my derivative, that value should be 0. Now, if I continue to trace the graph left to right, on this interval here, as I trace left to right, I'm increasing. So I'm increasing on the interval from 1 to infinity. So that means the derivative is going to be positive or greater than 0 on the interval 1 to infinity. So now, if I put this all together and graph this, look what my derivative is going to look like. It should be a line, 2x minus 2. So if I cross down here at 2, I'm negative from minus infinity up to 1. Then at x equals 1, I'm 0 because the derivative is 0 at 1. And then when I'm from 1 to infinity, I should be positive because my rate is increasing. So this right here, the graph of my derivative, I did it in different colors so you can kind of follow the intervals, but that's my graph of the derivative. And we checked it because we did this one previously. The derivative of this function, x squared minus 2x, when we use the definition, we got 2x minus 2. So these are the things you want to look for when you're sketching the derivative. Where is it increasing? Where is it decreasing? Where is it 0 on the function? And then you can apply that to sketching the derivative. Let's look at this one. This is just some generic f of x. So again, I'm going to try to color code this. I'm going to use red where the derivative is 0. I'm going to use blue where the graph is increasing. And I'm going to use orange where it's decreasing. So as I trace f of x, I'm decreasing from negative infinity up to about, it looks like negative 2. Then at negative 2, if I imagine the slope at that point of the tangent line, I would get a horizontal line, and the slope of a horizontal line is 0. So at x equals negative 2, my derivative is going to be 0. Then I'm decreasing from minus infinity up to negative 2. Now let's keep tracing. I'm increasing. Going left to right, I'm going up from here to here. So on the interval from negative 2 to 3, my derivative is going to be positive. And then at this point right here, my derivative is going to be 0 because that's, again, where I have a tangent line that's horizontal. And then my horizontal lines have slopes that are 0. And then lastly, I'm decreasing from 3 to negative infinity. So let me write this down. From 3 to infinity. Then we're going to be increasing from negative 2 to 3. And then we also have another place where the derivative is going to be 0, and that's going to be at x equals 3. So now let me draw the sketch of the derivative. So this is where my derivative should be negative. This is where my derivative should be 0 and touch the x-axis. And this is where my derivative should be positive, so it should be above the x-axis. So now let's use this information to actually sketch the graph of the derivative. So from minus infinity to negative 2, since the function is decreasing, the derivative is going to be negative, which means below the x-axis. So it's going to come up something like this. Then at negative 2, the derivative is going to be 0 because we have a horizontal tangent line where the slope is 0. And then between negative 2 and 3, the function is increasing, which means the derivative is going to be positive because you have a positive rate of change. And we got to swing back down because then at 3 for x, the derivative becomes 0 again. And then from 3 to infinity, because the function is decreasing, the derivative is going to be negative, which means it's going to fall below the x-axis from 3 to infinity. So now this is just a rough sketch of our derivative. It looks kind of like, if we drew it smoothly, it kind of looks like a quadratic. Since this is just a sketch, we really don't know how high this graph goes up of the derivative. So it could come up like this, and come back down, or it could be shorter. So we can see the basic shape of the graph, but we won't have exact point values. Okay, now we're going to start talking about derivatives and continuity. Now that we know how to sketch the graph of the derivative, we can take a look at the behavior of these graphs of the derivative. And we're first going to consider the relationship between differentiability and continuity. We're going to see that if a function is differentiable at a point, it has to be continuous there. However, the function that is continuous at a point does not need to be differentiable. So in other words, looking at this theorem here, if a function is differentiable, then the function has to be continuous at that point. But the converse is not true. It doesn't work to say that if a function is continuous, then it must be differentiable. It only works in one direction. So I'm going to say if it's differentiable at A, then it's continuous at A. That's what this theorem says. And I want to stress again that that doesn't work the other way around. It doesn't work to say that if a function is continuous at A, then it's differentiable at A. So I'm going to put a line through this to show that that's not true. This is false. This is true. So for a function to be differentiable at a point, we'll call it x equals c, there are three things that need to happen. Number one, f of x needs to be continuous at x equals c. But the other things are we can't have any points or cusps at that point x equals c. And by a point or cusp, I mean something that looks like this. There's a point or a cusp, looks something like that. If we have this behavior of the graph at x equals c, a point or a cusp, then it's not going to be differentiable, and I'll show you why in just a minute. And then the last thing, we need to make sure that there are no vertical tangent lines on the function at x equals c. So it needs to be continuous, and these things need to happen. So the first example of something that is not differentiable at a point C is this absolute value graph. At x equals 0, we have that the graph is continuous at that point, but it is not differentiable. So this is a perfect example of why the converse of this theorem doesn't work. In order for a function to be differentiable, it has to be continuous. But if it's continuous, it doesn't have to be differentiable. And that's this case right here. It's continuous, but it's not differentiable at x equals 0. And here's why. So as you can see, I have the graph of the absolute value of x here in black. And then I have the secant line in red. And as I traced point B along the graph of the absolute value of x, and I get closer and closer and closer to A, you can see that on the right-hand side, if B approaches A on the right-hand side, then we get a line that has a positive slope, and if you check it, you can see that the slope is 1. So coming from the right-hand side to the point 0, the limit of the slopes of the secant lines is approaching positive 1. But now if I'm coming from the left and I'm tracing point B on the secant line, so it gets closer and closer to A, you can see that the limit of the slopes of the secant line is approaching negative 1. The slope of that tangent line coming from the left-hand side is negative 1. So you have two different tangent lines at point A, one coming from the right and one coming from the left, and they have two different slopes. So the derivative isn't clearly defined at this value of x equals 0 on the absolute value. You can't have two different slopes for the tangent line and be able to graph that on the graph of the derivative and still have that graph of the derivative be a function, because you would have two different slopes for the same value of x. Now for the second graph here, this is the cubed root of x. This is an example where it's continuous, but not differentiable at x equals 0. And this is because at x equals 0, there is a vertical tangent line, which means the slope of the tangent line is undefined. So if we were to graph the derivative of the cubed root of x, there would be no value at x equals 0 on the graph of the derivative because it's undefined. Now let me show you how this works. Now for this example, for the cubed root of x, you can see I have point A and point B. Point A is at 0, 0, and then if I trace point B along the curve, so the distance between A and B is getting smaller and smaller, and we get closer and closer to having a tangent line rather than a secant line. And you notice when that happens, at x equals 0, we have a vertical line. And so if I were to try to graph the derivative of this function at x equals 0, the slope would be undefined. At x equals 0, it too would be undefined. And that happens as I approach from either. We have a tangent line that has an undefined slope. So when I go to graph the derivative of the cubed root of x, the graph is going to be undefined at x equals 0. Okay, so now we're going to talk about continuous and differentiable of piecewise functions. Now, when we're looking at a piecewise function, in order for the pieces to line up at points that are continuous and differentiable, when those pieces line up, they have to connect. Those two pieces need to connect, have that same value, and be smooth. So the differentiable ensures that it's smooth, because remember, if it's not going to be differentiable if there's a corner or a cusp there. The continuity forces the pieces to connect, and then the fact that we're going to make it differentiable will make sure that it has a smooth transition. So imagine that you're riding on a roller coaster, and the shape of the roller coaster is the absolute value of x. That's not going to be smooth. You're not going to want to hit that bottom point and then ride back up. You want a nice smooth curve, and that's what a differentiable function does. It makes the function smooth. So we want to find values of b and c in that first piece so that we get a function that is continuous and differentiable. So the first thing we're going to address is the continuity. To make sure that we find values of b and c so that these pieces line up and it's continuous with no holes or breaks or anything in it, we want to make sure that those two equations, these two pieces, I'll color code it to piece number 1 and piece number 2. We want to make sure that piece number 1 and piece number 2 are equivalent at that value, x equals negative 10, because those are where the values are going to connect at x equals negative 10. So we want to set up an equation. So we're going to have 1/10 x squared plus bx plus c. We want it to be equal to the second piece of negative 1/4 x plus 5/2 at the point x equals negative 10. So the first thing I'm going to do is plug in x as negative 10. And when I do that, I get 10 minus 10b plus c equals, and then when I plug in negative 10 for this x on the right-hand side, that's going to give me a 5. All right, now if I clean this up a little bit and I solve it for C, and I'm going to solve it for C because I know I'm going to do a substitution later and I know this ahead of time. If you were doing this blind, you would eventually go back and realize that you need to solve for C for substitution. So when I solve this for C, I'm going to get 10b minus 5. So I just combined like terms and isolated my variable for C. So this equation here is going to ensure that the function is continuous if this is satisfied. Okay, now to make sure that it's differentiable, we want to make sure that it's smooth. And so what we need to do is make sure the derivative coming in on one side has the same slope as the derivative on the other side. We want the derivatives of those two sides to match up as well. So if you think back again to our absolute value example, remember on one side, when we were approaching 0, one side, the tangent line had a different slope than coming in from the other side. We want those tangent lines to be the same and have the same slope. So in order to make that happen, we need to show that the derivative of one piece at x equals negative 10 is equivalent to the derivative of the second piece at x equals negative 10. So let's look at the first piece first. So looking at the first piece, so this is to show differentiability. Using the definition of the derivative, that the derivative at x equals negative 10 is going to be the same for each piece. So using the definition, I'm going to have the limit as x approaches negative 10 of the function, which is 1/10 x squared plus bx plus c, and we want to subtract the value of the function. Now we want the value of the function to be the same as well, and when we plug in f of negative 10 up here, we get out 5. So we want to make sure that that value is the same as well. So I'm going to subtract 5 all over x minus a negative 10, so this is going to make it a plus 10. So all I did right here was set up the definition of the derivative. And if we recall, that would be the limit as x approaches a of f of x minus f of a all over x minus a. And we're doing this for the first piece. So this is going to get messy, but not hard. It's just messy. Okay, now I can't use direct substitution here. And I also want to get rid of that complex fraction, get rid of the fraction within the fraction. We have a 1/10 up there. So I'm going to multiply both the top and the bottom by 10. So I have the limit as x approaches negative 10. And when I multiply the top and the bottom by 10, that's going to give me x squared plus 10bx plus 10c minus 50. And that's all over x plus 10. And I have to multiply the bottom by 10 as well, so I have a 10 out in front here. So from this step to this step, all I did was multiply by 10 to clear that complex fraction, that 1/10. Now, I'm going to do a substitution to try to eliminate multiple variables. We know that c, from up at the top, c is equal to 10b minus 5. So I'm going to have the limit as x approaches negative 10 of x squared plus 10bx plus 10 times, and then I'm going to replace c with 10b minus 5. And then I subtract 50 all over 10 times x plus 10. Now, when I distribute that 10, I get x squared plus 10bx plus 100b, then minus 50, and another minus 50 gives me minus 100, all over 10 times x plus 10. Now I want to try to factor this so that I can get rid of that x plus 10 in the denominator, and I can go ahead and use direct substitution. And I just realized that I accidentally dropped my minus, so let me fix that. So the limit as x approaches negative 10 for both of these. Okay, so now if I do a little bit of rearranging and I do factor by grouping, I can get x plus 10 times x minus 10 plus 10b, and that's all over 10 times x plus 10. So now I have it where I can cross off my x plus 10s. And I'm left with the limit as x approaches negative 10 of x minus 10 plus 10b all over 10. Now I can go ahead and do direct substitution. And when I do that, let's see, that's going to give me a negative 20 on top plus 10b all over 10. And when I divide that out, that's going to give me a negative 2 plus b, or you can write it as b minus 2, which is probably easier. Okay, so now we've got another equation. We've got b minus 2. So we're getting down to where we can solve for b and c. We're getting closer. That is just one side. All we did was show what the derivative was coming from the left because we did the first piece. Now we want to show the derivative for the second piece, and we want to make sure that those two derivatives are the same and they line up. So for the second piece, actually I made this piece green. I want to show that the derivative at negative 10 for the second piece is the same. So I want to do the limit as x approaches negative 10 with the second piece, which was negative 1/4 x plus 5/2 minus the value of the function, which is 5, all over x minus a negative 10, which would make it a plus 10. Okay, now I want to clear the fractions and try to simplify a bit. So I have the limit as x approaches negative 10. I'm going to multiply everything by 4 because that will clear my fractions. So that will give me a negative x plus 10 minus 20 all over 4 times x plus 10. So now I have a negative, let's see, how can I factor that? That would be a negative x plus 10 in parentheses all over 4 times x plus 10. I can cross that off and I get that the limit as x approaches negative 10 is negative 1/4. So this is the derivative for the second piece. This is the derivative for the first piece, and those have to be the same. So if I set those equal to each other, if I have b minus 2 is equal to negative 1/4, then b has to be 7/4. And then I can use substitution and go ahead and plug back in. We had that formula up here for c. If I plug that back in for c up here, right, we have c equals 10b minus 5. I'm going to plug b in, and I'm going to get that c is equal to 10 times 7/4 minus 5, and that's going to give me 25 over 2. So now we have our values for b and c. So our final answer, after all that work, that was long, but not hard. It was just long. So let's make a note over here. Our function would look like this. 1/10 x squared plus 7/4 x plus 25 over 2. Let's see, that's when x is less than negative 10. And then we have negative 1/4 x plus 5/2 when x is greater than or equal to negative 10. This function now is going to be differentiable and continuous at x equals negative 10. Let's take a look at this on the graphic. All right, so let's go ahead and graph this function that we came up with the values of b and c to make sure that this works. So I'm going to put in parentheses 1 divided by 10, and then x squared. And we're going to add that to 7/4 x, and then add 25 over 2. I'm going to close parentheses, and then I'm going to tell the calculator I want this on the interval. Let's see, when x is less than negative 10. And then close parentheses. That's the first piece. Then the second piece is negative 1/4 x plus 5/2. And I'm going to tell the calculator to do that on the interval when x is greater than or equal to negative 10. So I'm going to go back to my catalog and find greater than or equal to. Here we go. And then negative 10. Whoops, I forgot my parentheses. Let me insert that. Close parentheses. Okay, so there's our piecewise function. Then I'm going to set my window. Since I want to see further than negative 10, because negative 10 is the point that we're interested in, let's go out to say negative 20. And let's say we do this on a scale of 5. And let's do maybe negative 20 to 20 for our y-axis on a scale of 5. Let's see if that shows us what we need. There we go. So there's my first piece. That's the quadratic. And then the linear function, negative 1/4 x plus 5/2 is this in red. Now let's zoom in to see, get a better look at that point and see if it matches up the way we would hope. From far away it does, but let's take a little bit of a closer look. No, it looks like it does. So we did a good job. We found the values of b and c so that it's continuous and the pieces line up without any holes or breaks. And then we also made sure that it was differentiable so it was nice and smooth. Okay, the last topic in this section. I know this section has a lot of topics, but the last topic we're going to cover is what's called higher order derivatives. And that's the idea when you take a derivative of a derivative. And so when you take a derivative of a derivative, that's the second derivative. If you take a derivative of the derivative of the derivative, that's a third derivative, etc. Now the notation for these higher order derivatives look like this. So we said f prime is the first derivative. But we can also put more of those little slashes up there and make it look like double prime for the second derivative. And we can do 3 for the third derivative. And then if you get anything higher than 3, typically you just put in parentheses so you don't have too many dashes what the derivative is. So that would represent the fourth derivative. And so you could keep going. So up to the third derivative, you can use the little prime symbols, the little slashes up there. And then after that, just use parentheses with the number derivative in it. And then that goes for the y notation as well. So if I wanted to, for example, find the third derivative, but the notation we're using is y, we would do this. Okay, and then another notation. Remember, we had the dy dx. This was the first derivative. Now, if we want a higher order derivative, we would put on the top, let's say we wanted to do the second derivative, it would look like this. And then on the bottom, it would look like this. And then for the third derivative, same thing, but you would just replace the 2 with the 3, so it would look like this, etc. Okay, so let's look at our first example. We're going to do 2 examples of higher order derivatives. Okay, so this first example is f of x is equal to 2x squared minus 3x plus 1. So we're going to find the second derivative. So we need to find the derivative and then take the derivative again. So first, let's find the first derivative. So we're going to do the limit as h approaches 0 of f of x plus h minus f of x over h. So we're going to do the limit as h approaches 0 of 2, and then in parentheses I have x plus h squared minus 3 times x plus h plus 1, and then I subtract the function, which is 2x squared minus a minus 3x gives me a plus 3x. And if I subtract a 1, that gives me minus 1. And then this is all over h. Now I'm going to multiply out. So I have x plus h squared. I got to square it and then multiply by 2. When I do that, I'm going to get 2x squared plus 4xh plus h squared. And then I subtract 3 times x plus h. So I have minus 3x minus 3h. And then I have the plus 1. And then I go to subtract 2x squared plus 3x minus 1 all over h. So big mess. Now, when we clean this up, let's see, I can cross off the 2x squared. I have a minus and a positive 2x squared. I can get rid of the plus 3x and the minus 3x. And I can get rid of the plus 1 and the minus 1. So a lot of things start dropping out. So a lot of things start dropping off as long as you make sure you distribute your negative correctly. It should drop off. All right, so what we're left with is 4xh plus h squared minus 3h all over h. So now, if I divide everything by h, I factor out an h on the top and then divide it off the top and the bottom. So I factor out an h on the top and cancel it with the h in the bottom, and I'm left with 4x plus h minus 3. And I don't need an h down there anymore because I canceled it, so I got a 1 down there. Now I can do direct substitution and plug in 0 for h, and I get that the first derivative is 4x minus 3. Now let's find the second derivative. So the second derivative is if I take the derivative of the derivative. So I'm going to take the limit of f of x plus h minus f of x all over h. If I plug in f of x plus h, that gives me 4 times x plus h minus 3, and then I get to subtract the function, which is minus 4x plus 3, because remember you're subtracting this whole thing. So remember to distribute your negative, and that's all over h. I'll continue down here. So I get the limit as h approaches 0. If I distribute that 4, I get 4x plus 4h minus 3 minus 4x plus 3 all over h. Now I can start crossing stuff off. The 4x and the minus 4x disappear. The 3 and the negative 3 disappear. So now I'm left with 4h over h, which is just 4. And so this is one of our basic limit laws. If I take the limit of a constant function, I'm just going to get 4. So this is the derivative of the derivative. This is the second derivative. It's not hard, it's just long and messy. Okay, lastly, we're going to talk about the second derivative in terms of position functions. So when we take the first derivative of a position function, we are talking about the change in position, which is your velocity. So it's the change in distance over the change in time, which is your velocity. Now, if I take the derivative of the velocity, that's the rate of change of the velocity, which is acceleration. So when we take the second derivative, and then we're dealing with position functions, what we're really finding is the acceleration. So here's our position function that's given in this question. I want to find the acceleration, which would be the second derivative. So we're going to first find the first derivative, which would give me the velocity. I'm going to find the limit as h goes to 0 of s of t plus h minus s of t all over h. Now notice I'm not using f or x here because our variables and the name of our function is different. So I just swapped them out, but it's the same idea. So down here, I'm going to plug in t plus h everywhere I see t in my function. So I have 3 times t plus h squared minus 4 times t plus h plus 1. And then I got to subtract the function. So that's minus 3t squared plus 4t because I got a double negative, and then minus 1 all over h. Now at this point, we've had enough practice where I feel pretty comfortable skipping a couple steps. I'm going to let you do the in-between steps. I'm going to let you finish it from here. You want to find the product. You want to square the t plus h, FOIL everything, combine like terms, and then once you can factor and get rid of that h in the denominator, you're going to find that the limit is equal to 6t minus 4. So take a minute, pause the video, see if you can get that answer. Then when we go to find the second derivative, which is the acceleration at a particular time, we're going to take the limit as h goes to 0, and we're going to find the derivative of the derivative. So we're going to plug in t plus h into the function, and then I'm going to subtract the function and divide by h. So now when we combine like terms, factor, and do all that stuff and simplify it, what we're going to get is the limit as h approaches 0 of 6, which is of a constant function, which is just 6. Now, because the problem says that the distance is in meters and the time is in seconds, my units for acceleration would be meters per second squared. And my velocity would be meters per second. So this allows us, let me highlight it, this allows us to find the velocity at any moment for that position function. And then this tells us that it doesn't matter what the position is, that the acceleration is